Well, firstly, thank you very much for having me, and I'm delighted to be here and talk to the Royce Institute. Also, thank you to everyone who is still here. I know there's been a lot of talks, a lot of information, so I appreciate sticking around to hear what I have to say. So I'm going to start by just talking a little bit about the history of Polaron, where we come from. I think a slightly different perspective from the rest of the speakers, where we have more of an industry perspective, bit of experience in working more with kind of commercial in the commercial world of modeling, and also interesting story of how we came to be from academia and now into industry, that transition. So our origin story is that we were well, we are a spin out of Imperial, where I did my PhD with Dr. Sam Cooper. We were working on developing these technologies around using AI for battery material characterization and design. And actually, the origins of our research are papers that we published over the last kind of 4 or 5 years. Myself, my co-founder, Dr. Steve Kench, we were working on these ideas in a very typical academic way, publishing papers, working with collaborators. But we realized that we had quite a lot of interest in our research from industrial collaborators, companies, battery companies that were interested in what we were doing and could see a lot of value in applying the techniques to their materials development. And that's why we decided to spin out at the end of last year and take our technology and try and turn it into a product, which is a very different type of activity than writing a paper. And to do that, we have a great team of engineers, machine learning engineers, and also lots of material science understanding, because the problem that we're trying to solve is still fundamentally quite scientific and requires a lot of understanding of the principles and the kind of robust and reliable outputs that we are trying to provide to our customers requires this kind of super detailed, super technical understanding of the problem. So what is the problem that we're trying to solve? Well, I think everybody, the way that we frame material science problems, everyone is roughly working to the same heuristic, which is that we want to design better materials at an affordable cost that solve the problem very well, that have the properties that we want them to have, that can be designed in a way that is manufacturable. And one of the ways that we understand this is through the relationship between the process, the manufacturing process, how we make these materials, and their structure. Could be microstructure, could be the structure at the atomic scale, which we've seen some people talk to today, or it could even be macroscopic features that we can observe with the human eye. But this process to structure relationship is super important. We know that the structure often mediates a lot of the performance that we're interested in. So we want to learn this relationship between process structure and performance, but it's super complex. And you've seen some of the talks today talking about how complicated it is and how difficult it is to model that using kind of more classical modeling techniques, finite element, nonlinear solvers. It's a very complicated physics with lots of moving parts. And so what we're trying to do is take that complex problem and solve it with machine learning by not just directly going from process to performance, but actually going from process to structure and being able to predict the structure of materials and how that varies with process using machine learning and image data. And we know this is a really important problem. We've seen the impact that this has in industry. So if we zoom out from the academic world a little bit and we look at what's the impact that this has on manufacturing companies, well, we know it costs them a lot of money to do this process and performance mapping by trial and error, which is actually what the kind of state of the art is in industry. Is we make stuff, we test it, we see how it works, and we go back and we make some more. And this is leading to a competitive disadvantage and a kind of a friction to developing new technologies and pushing these new technologies into the market, which we need to tackle some of the critical problems of today. So we are going about this in a way where we're focusing on image data and that idea of microstructure as being the core link between process and performance. And so that's not true of all materials, but for the materials that we're working on, this is true. And specifically, we have a focus at the moment around battery materials. And so with a battery electrode, we have this porous microstructure in the electrode, and the relationships between the particles, the different phases, the geometries of these electrodes has a really strong impact on the performance, things like the energy density, charge time, kind of actually the performance of how the cell performs in a car, how far can you drive and how quickly can you charge your car. And so the first step in making the best use of image data is to analyze the image and to take a raw image from a microscope and turn it into something that is computationally relevant. And to do this, we need various tools. One of the core tools is what we would call segmentation. So taking that raw image and labeling each pixel with which phase it belongs to. Now, it seems like a simple task, but these images are often highly complex and lots of the phases look the same. It's not very straightforward. So we have developed a segmentation method that uses latest vision transformer technology, these feature foundation models that are developed for solving very big, complex image tasks. And we've adapted them to microstructure tasks like this. And this means that we can reduce the image labeling time. And also we've enabled all of these tools in the cloud. So none of this has to happen locally on your machine. You don't need access to a big computing cluster. All of these operations happen in the cloud, and we can manage that complex compute demand on our side. And that's one of the core value propositions of Polaron, is that we know that a lot of these machine learning tools are not so easy to get started with. Not everybody knows how to code. Not everyone has access to this, the compute infrastructure. And so we're trying to take some of the complexity there away. And here are some of the outputs of our segmentation model. And we can see here two slightly different tasks. And in both of these tasks, we've got complex microstructures with features that are not easy to extract in an automated way. So on the right-hand side here, you can see the cracks in the microstructure being labeled differently to the particles and differently to the background or the pore phase. And actually, the cracks and the pore are empty space, and they look very similar through a microscope. They have the same grayscale values, but with our machine learning approach, what we're doing here is learning not just what the value of the pixel is, but also how it relates to the pixels around it, how kind of semantically, what does it mean to be that pixel, what is the feature it belongs to, and where it is in the image compared to the other features. So it's learning something more complex and more sophisticated than just what is the value of the pixel. The next thing that we've solved using machine learning, which is important in this process structure performance mapping, is that we often know that 3D structures and 3D properties are the things that we're interested in. So for a battery material, transport properties, how easy is it for things to flow through our materials, diffusion properties, conduction properties, those are the things that actually mediate the battery performance. And we need 3D structures to do this. But one of the big problems we came up against is 3D imaging of microstructure is really challenging for materials at this length scale, and especially for multi-scale materials as well. But 2D imaging is often cheap. Often we see that labs have access, and this is not just academic labs, this is industrial labs as well. They have access to SEM machines or optical microscopes and can take 2D images quite well, but taking 3D images using cross-section, serial cross-sectioning fib or XCT, it's very expensive. They don't have the equipment. They have to rely on external partners. It's not so easy for them to do. So what we developed was a 2D to 3D reconstruction technique that takes a single 2D image of a material, a cross-section, and we're able to reconstruct from that single image what it would look like in 3D. Now, this happens very quickly, and comparing it to doing a 3D imaging technique, it's hundreds of times faster and saves a lot more money because we just take a low-cost 2D image and we can now reconstruct any size volume 3D that we want. And this is all done through a data-driven approach. There's no physics-based modeling here. We're not imposing any kind of statistics on it or trying to fit shapes to it. It's purely learning from the data that it sees in the image. And we've applied this to a very wide range of materials. So I've focused mainly on battery materials so far, but we applied this exact same technique across a large database of metal alloys, composites, ceramics, and we found that the technique performs very well. And we did some validation of these reconstructions, and the validation we do is we take a 3D image, we take a slice through it, we train our model with that slice, we compare the reconstruction to the ground truth 3D, and we look at the statistics, and we see that there's incredibly good agreement. The final step is, can we connect this image data that we know is linked to the process back to the performance of our material, and then optimize to identify the best process parameters that give us the best structure, that give us the best performance. And we have developed a methodology that uses this 2D to 3D reconstruction algorithm as part of a way of learning the relationship between process and structure. So we take image data collected under different process parameters. So in this case, we varied the mixing and the calendaring process. So we take some images under varying mixing and calendaring, and we train a model that then can predict how the structure will change as we change those parameters. And we can generate a structure in under a second, this prediction. If you think about how we would model that with physics, if we were doing molecular dynamics simulations or any type of kind of thermodynamic or finite element model here, that would take a lot longer because we have loads of interacting atoms, but we're learning all of those through machine learning, which allows us to predict in a matter of seconds. And this enables a rapid optimization loop where we predict the structure. We can then extract properties from the structure that allow us to simulate the performance. In this case, we're doing an electrochemical simulation of a lithium-ion battery cathode. So we can predict how that cathode would behave as we do an electrochemical charge or discharge. And then we can do a Bayesian optimization analysis where we search the space of possible process parameters and then identify the process parameters that give us the structure with the properties that give us the best discharge simulation. And so in under a day, we managed to identify a optimal process parameters pair that gave us a performance that was actually a 10% increase on the original design that we had. And here we can see some of the results. It's not just about finding the best material you possibly can find in the best possible process, because we know that actually the way we design materials is more nuanced than that. In fact, we have various load cycles on the battery and also different applications that might need different designs. So here we can see some of the results from the optimization. And what we did here is we varied the power that we applied during the charge and the discharge, and we're trying to maximize the capacity of the cell. So you can see here that in the top left, we've got the low power situation. In the low power situation, the simulation tells us that what we want is a high active material weight percent. So this means we want to pack the electrode full of the active material, in this case NMC, and that means that we'll get a higher energy density because we have more of this active material. And we also want a low porosity. So this means kind of calendar it more and don't have as much gaps in the porous structure, because at low power, we're not driving the cell very hard. There's not a lot of current. And so what we're doing there is we're not rate limited by diffusion. As we increase the power, our prediction says, our optimization loop says, move that the optimal parameter pair to low active material weight percent and high porosity, because as power becomes higher, that means our rate limitations become more important, because we're starting to get diffusion limitations and transport limitations in the cell, and therefore we need more porosity to allow transport through the networks, and less active material weight percent and more binder in our solid fraction, so that we can facilitate the electronic transport as well. So you can see here how we create a flexible design tool for different application scenarios. And here we can see the two cells that we designed using this technique, one for high power, one for high energy. And one of the nice kind of outcomes here is that we can actually see what the cell looks like, because we're predicting the structure of the cell and how that changes under these different parameters. We're building all of these tools into a software solution for researchers in academia and also in industry to make use of these tools so they can train their own AI models. Because we think it's really important to be able to give these tools to people to use. Not everyone has, like I said, the experience or the understanding of machine learning to be able to code these from scratch or run them on their own machines. And so these image processing, reconstruction, and process structure optimization tools are being built into a platform that allows you to manage your microstructural image data, label it, filter it, and store it, whilst also facilitating this AI model training in the cloud. Like I mentioned, is a very data efficient approach. So we can actually get started with a single image. You don't need thousands or millions of images to use these techniques. And that's because we've developed these algorithms to be compatible with the materials data sets that we've seen in academia initially, and now that we're transitioning more into industrial applications. So hopefully you'll see the value in what we've built here is that it allows you to ideally prototype less, because if we can explore this space of possible designs and process structure performance pairs in silico in our simulations, that means that we can explore the space more without having to make as many samples. And also we can gain deeper insights about our materials through this AI-driven image analysis and image reconstruction techniques. We can actually reconstruct 3D volumes of materials that have never been imaged in 3D before, and that's really exciting as well. And ultimately, this allows us to make better materials, to identify designs for materials that deliver higher performance, and do that at a reduced cost, because we are shrinking the time it takes to go from initial data to design. Thank you.